Let's go to the example for the analysis of sections. Okay, so please everyone follow me. So this is the example 4.1, the first example. Okay, so the cross-section of rectangular beam is shown in the figure below using stress block diagrams, and the following data determine the area and the number of required reinforcement, which we need to calculate the AS. Okay, so first you can see that the B and the D, B is 250 millimeter and D is 450 millimeter. Okay, so this line is the neutral axis. Okay, so design moment provided is 200 kilonewton meter. Okay, MED design. Okay, characteristic strength of concrete FCK is 25 Newton per millimeter square. Characteristic strength of steel is FYK 500 Newton per millimeter square. So you can see that the K stands for the characteristic strength. Okay, and then so first we need to calculate the ultimate moment resistance of sections, which is the M balance. Okay, so M balance is equal to 0.167 FCK B times D power of 2. So you put in the value of 0.167 times 25 Newton per millimeter square for the FCK, and B is the 250 and D is the 450. Okay, then this is 450 power of 2, sorry. So you calculate, you will get this value 211359376 Newton millimeter square. Okay, and then you change the unit to kilonewton meter, you will get 211.36 kilonewton meter. Make sure you don't get mistake at the conversions. Okay, so 211.36 kilonewton meter is greater than the design moment 200 kilonewton per kilonewton meter. So it is singly reinforcement because M is less or equal than M balance. So this is the ultimate moment resistance. Okay, so the moment design moment is less than the ultimate, so you can just use singly. So if let's say M is greater than M balance, so you need to use doubly. So for this example is singly reinforcement. Okay, so neutral axis X. So now we need to get the X value. So we know that M is equal to 0.45 for FCK BX times D minus 0.4x. So this is all in the theory explanations. You can get the get this equation, all this from the previous explanation on the theory for the slide. Okay, so you substitute the value of M and then the value of FCK P, okay, and then X, and then D is 450 minus 0.4x, you will get these equations. Okay, so you sort it out accordingly, and then you will get x squared minus 1125x plus 176.252.5 equal to 0. So this one you can solve it and then you can get the x because the unknown only 1. So you either can use the calculator to get it, or either you can use the quadratic formula to solve it. Okay, so what is the equation? So you know that x equal to negative b plus minus in the square root, okay, b power 2 minus 4ac over 2a. I believe every one of you are familiar with this. This is you learn from the mathematics, so I'm not going to explain more. Okay, so you substitute the value accordingly. Okay, follow my step, then you will get x is equal to 188 or either 937. So for this we will use x equal to 188 because the because the D is only 450, so it is 188 from the top to the neutral axis. Okay, so x is equal to 188 for the centroid, so we need to check. X over D is 188 over 450, so equal to 0.418, which is less than 0.45 that suggested by the Eurocode. Okay, so 0.42 is less than 0.617, so it is under reinforcement, so it is okay. So remember, for design purpose we must use under reinforcement. We cannot use over reinforce or under balance. Okay, so after that we need to calculate the lever arm Z. So Z is equal to D minus 0.4x. So you substitute the value of D and X, you will get 374.8 millimeter. So therefore the area of reinforcement, now you get the area of reinforcement is equal to M over 0.87 FYKZ. Okay, so you substitute the value, design moment M, and then 0.87 times the FYK 500 times the Z value 374.8. Then you will get the AS required is 122.7 millimeter. So we want to use the diameter bar is 20 mm. Okay, you check, refer to the table 1. Okay, the table 1 in the table 1 cross-section area, okay, in the Euro code at the behind there, the appendix there, you can find it. Okay, cross-sectional area. So 1226.7 over 314.2, 3904 is 4 bar. Okay, so 4 times 314.2 is 1256.8 millimeter. So it's equal to 1257 millimeter. Okay, so AS provided 4 hash, okay, 20. AS provided is 1257. The required is 1226, and then you check from the table 1. Okay, the AS provided must be higher than the AS required. Higher a bit, same or higher. So 1257 you provided. So means that for this rectangular beam you are going to provide the 4 hash 20 at the bottom for the singly reinforcement. So that's it for the example 1. So now let's go to example 4.2. So figures below shows the cross-section of a singly reinforced beam. Determine the resistance moment, okay, for the cross-section with the assistance of a stress plot diagram. So given, okay, B is 250 and D is 450. FCK is 25 Newton per millimeter square. FYK is 500 Newton per millimeter square. So the AS is, okay, 2 times pi 25 power of 2 over 4. This is the area. Okay, how you calculate the area? Because they're given 2 hash 25. So you times the cross-section area for 2 diameter, you will get the AS. So AS here is 982 millimeter. Okay, so here, okay, there's a line here supposedly, but then you cannot see it here. So let me draw. Draw it. Oh, it's not able to show. Oh. Okay, sorry, it's come out too many lines here. So let me delete this. Okay, so let me draw the line here. So this is the neutral axis. Okay, bear with me if the line is not really straight. So okay, so value of x, okay, x is 0.8x. So let me change to the laser pointer. Wait a minute. Okay, so here is the 0. This is the stress plot diagram, yeah. So here at the top is 0.567 FC, and FCC is 0.45 for FCK times BX, and this is the neutral axis. Okay, this is the neutral axis at here, and Z is D minus 0.4x, and FXT is 0.87 FYKAS. Okay, so this is a stress plot diagram. So this is the FST, this is the FCC. Okay, so all this slide I have given in the PDF format also, so you can go through it if this is not really clear because I scan it. Okay, so for equilibrium, okay, total force in the section should be 0, means that total section of top and bottom should be 0. So FST is equal to FCC. Okay, so 0.87 FYKAS, which is the FST, is equal to FCC 0.454 FCKBX. Okay, so if in the equilibrium, okay, so X, so you organize it, you put in the formula, you can see that, okay, X is equal to 0.87. You put this, remove this, and then you rearrange this, you will get X equal to 0.87 FYKAS over 0.454 FCKB. Okay, so you have the value of FYK, AS, FCK, and B. So you substitute all the value, you can get X equal to 151 millimeter. So after you get the X, you will check X over D is 151 over 550. So it's 0.335, which is less than 45, 0.45. So it's okay. Okay. So FCC is 0.454 FCKBX and Z is D minus 0.4x. So now we go to calculate the moment resistance of sections. So moment resistance of section is equal to FCC times Z or either FST times Z, because now it's in the balance. Okay, we calculate equilibrium, so you use either one is okay. So now we use the FCC times Z, you will get 0.454 FCK BX times D minus 0.4x. Okay, so you substitute the value inside it, you will get 166.93 kilonewton per kilonewton meter. Okay, so for stress block, X is 0.8. So for the stress block, you need to substitute all the value inside it, right? So you calculate the X is equal to 0.8x. So you get 120.8 millimeter. And 0.567 FC is 14.175 Newton per millimeter square. So FCC is 428 kilonewton per millimeter square. And Z is 389.6 millimeter, and FST is 427.17 kilonewton per millimeter cube. Okay, so that's it for this example. Now, guys, let us look at example 4.3, which is the example for doubly reinforced beam. So the cross section of rectangular beam is shown in the figure below. So using the data given, determine the area and the numbers of required reinforcement. So again, B is 250 mm and D is 500 mm. So MED, the design moment, is 450 kilonewton meter, and characteristic strength of concrete is 25 Newton per millimeter square, and characteristic strength of steel is 500 Newton per millimeter square, and the D prime is 50 mm. So the ultimate moment resistance sections, the M balance we need to calculate is 0.167 FCK B times D power of 2. So you substitute the value of FCK, B and D inside, you will get 260.94 kilonewton meter. So now the ultimate moment resistance for this is less than the MED. It's smaller than the value of the moment design moment. So when the M design is greater than the M balance, the ultimate moment resistance, so you need to have compression reinforcement. Means that these sections need extra steel on the top here. Okay, so next. So area of compression reinforcement. So now we need to get the AS prime, which is the AS on top. Okay, so we need to use the equations M minus M balance over 0.87 FYK D minus D prime. Okay, so you substitute the value of M balance, FYK, D, and D prime. So you will get the value of AS prime is equal to 966 mm, and check D prime over X ratio. So X is equal to 0.45 D. So 0.45 times 500 is 225 mm. Okay, so D prime over X is 50 over 225, which is 0.22 less than 0.38. So compression still achieve its design strength at 0.87 FYK. So means it's okay. Okay, and then area of tensile reinforcement. So we already got the area of AS prime, the compression steel. We also need to determine the area of tensile reinforcement, which is the reinforcement at the bottom. So AS equal to M balance over 0.87 FYKZ, okay, plus AX prime. Okay, so it's equal to 260.94 times 10 power of 6. This one is for the unit conversion, you can calculate it, and then you substitute the 0.87500 times for the value of Z41, or where I already stated here how you calculate the Z. Z is equal to 500 minus 0.42 times 225, so you get 410. So you substitute the value inside, you calculate, you solve it, you get AX equal to 2429 millimeter square. So we provided here is by using the table 1, which is the cross-section area of reinforcement at the last page in British Standard Eurocode 1992 Eurocode 2. Okay, you check the book that the Eurocode 2 books, okay, which is the one that you got it from the Mr. Cole. Okay, so you will get 2H25 as prime provided is 982 millimeter square, and 5H25 as provided is 2455 millimeter square. Again, the as provided must be higher than the as required. Okay, so now let us go to the example 4.4. So example 4.4, let us look at it. It is calculate the moment resistance of the doubly reinforced sections as shown in the figure below. So B is 250, and then D is 500, and then the D prime, which is from the top, the surface of top to the diameter at the center of the compressive reinforcement center, which is the 50 mm. Okay, so characteristic strength of concrete is 30 Newton per millimeter square. So now the concrete we use is 30 Newton per millimeter square, different from the previous examples. And the characteristic strength of steel is still FYK 500 Newton per millimeter square. The D prime is 50, so as mentioned here. So AX prime for 3H20 is 943 millimeter square. Okay, so this is given. AS is 5H25, which is 2455 millimeter square. This one you can calculate manually by using the equation. So either you can refer to the books, okay, to the table 1 that in the Eurocode 2, the appendix there. Okay, so you will get a value of this AS prime and AX. So now we calculate X. Okay, so the X value is using the equation that I already explained in the previous section before, also in this equation, 0.87 FYK AX minus AX prime, okay, over 0.454 FCK times B. So you substitute the value inside, you will get the value of X equal to 193 millimeter. So checking X over D is 193 over 500, so it's 0.386, is less than 45, it means it's okay. And D prime over X is 50 over 193, which is less than 38. It's also okay. So the steel achieved its design strength at 0.87 Fy. Okay, so the moment resistance of sections, the M is equal to FXC Z1 plus FCC Z. Okay, FXC Z1, okay, which is this value plus FCC. Okay, so also equal to FST equal to 0.87 FYX. Okay, so we calculate this, you substitute the value of FCZ1 and FCCZ according to these equations, you will get moment resistance of section is 462.45. Okay, so this is the value of it, and this is the design. You just check in, so everything is okay. So let's So, okay, let's conclude here. You can see that I make a conclusion here for the analysis of section. So for the checking, M must be great. M for the design moments must be less than the M balance for the ultimate moment resistance, or K is less than K balance. So you will use singly reinforced rectangular beam. Okay, if the M is greater than M balance, which is the design moment is greater than the ultimate moment resistance, or either K is greater than the K balance, okay, so you need to use the doubly reinforced rectangular beam. Means you need to have the compression reinforcement. Okay, so for singly reinforced rectangular beams, okay, you need to get X and then check X over D is 0.45, and then you get Z. Okay, after you get Z, then you get AX required and AX provided. So for doubly reinforced rectangular beams, okay, after you calculate the M and M balance, you compare. If M is greater than M balance, then you calculate the AX prime. After you calculate the X prime, you get X prime over D is less than 0.38. If it is okay, then you can get the value of AX. So AX required must be greater than AX. AX provided must be greater than AX required. Okay, AX provided for the AX prime provided must be greater than the AX prime required. So you check it and then you get the dimensions of the bar. So that's it for analysis of sections. So see you in another topic.